Dear participants, our day and our second day of big journey through Open Readings Conference still continues. Here is the historic moment which was taken yesterday, as you see, with Gerard Monroe at his public lecture, and all photo credits goes to Nail Garayev. We're really thankful for his photos, and you can find it on Facebook. Tag yourself, yes, and still we encourage you to participate at our photo contest. Yeah, as you remember, I remind once again, hashtag FTMC, hashtag Open Readings. So, yes, the second one today at 5:30. Yeah, will be our scientific discussion between three scientists: Jocelyn Bell-Barnell, Kishan Dolaki, and Linas Vilchauskas, about the scientific career, its personal ups and downs, and living in between. What does it really mean to be a scientist? What is behind all achievements? What is the person? And here is the last one, new. So the abstract book you can find now at openreadings.eu.com. Yes, find the list of all participants and presenters. Okay, so that's all of information. Now I will give the word for our first moderator, chairman, Professor Gulbinės.
Good morning. I will shortly introduce Professor Anders Hagfeldt, who is one of the leading scientists in physical chemistry, and he is particularly well known from his developments of dye-sensitized solar cells. He is from École Polytechnique, from Switzerland, Lausanne, but he is originally from Sweden. He got his PhD obtained from Uppsala University in 1993. And then he went to École Polytechnique in Lausanne as a postdoc to the famous Gressel laboratory. And now he is in École Polytechnique again as a full professor. And he has laboratory of photomolecular sciences. Besides, he is also a visiting professor in Uppsala University and also in Nanyang Technological University in Singapore. He is also a member of several academies of scientists of Royal Swedish Academy of Science, Royal Swedish Sciences in Uppsala, Royal Swedish Academy of Engineering Sciences, and also European Academy of Sciences. He is a very productive scientist. He published more than 500 papers, and every year he publishes more than 30 papers, which are cited also very well, and he is one of the best cited scientists in physical chemistry. And totally his papers have more than 58,000 citations, and H index is 115. Moreover, he is an author of 9 publications, and also he co-founded Dynamo company dedicated to materials and equipment for solar cell applications. And today he will tell us how to make solar cells by ourselves.
Thank you very much, Professor Gulbinės. It's for a nice introduction. And thanks to all of you and for inviting me. I was very happy to get the invitation, because normally you go to your own kind of family and meeting the conferences, but here to be part of a student-organized meeting with different topics and so on, I felt was very exciting and interesting to be, and also to have the chance to, for the first time, to come to Lithuania and Vilnius. I'm from Sweden, Uppsala, and not far away from here actually, but it's the first time, and yesterday evening we had a walk through a very nice town of Vilnius. Coming to my talk, now I moved to Switzerland some 4.5 years ago. This is the campus of EPFL. We are in the lab of chemistry somewhere here. And then you have the Lake Geneva here with Montreux somewhere here. And the French Alps are on the other side of the lake. So it's a very nice place to be at. And if you have a chance and interested, you're welcome to get in touch and meet up at EPFL. My talk today will introduce a little bit on solar cell, what's happening, but very short, let's say a few statistics from the last years of installations and so on, and then I will go quite quickly into what we are doing in terms of dye-sensitized cell, to take you through that you can make it yourself in half a day, let's say, without knowing anything basically. We have even done it with school children at the age of 7 and 8, so they can do it. So it's an interesting technique from that point of view. But also, of course, take you to what we are doing in terms of research. And then the last years have seen a tremendous excitement in what we call the perovskite solar cell, which originates in a way from the dye-sensitized cell. So I will show you that bridge and also what we are doing, and research is done with perovskite solar cells. So to start with, I would say that we are seeing a huge change of our electricity production, and I saw this sometime, and things can happen very fast, sometimes big changes. So here is about the cars introduced in around the 1900, and if you take a picture of a street, I think this is New York, around 1900 there is one car you can find here among all the horse carriers. 10 years later, you find one horse together with all the cars instead. So even such big movement can happen in fairly short time. And maybe that is, in a way, something we are seeing when it comes to energy production. We have to see, of course. But the numbers look very interesting. This is the exponential growth of photovoltaic installations in the world from the last 10, 12 years. And it's an exponential growth with about 30 to 50% growth annually, let's say. And the last number we have seen is the end of 2017 with a total installation of 400 gigawatt in power electricity. That corresponds to about production of electricity from 50 nuclear power plants. And I think also at the end of 2018 we will see that we are probably over 500 gigawatt. So it's an exponential growth, and it's a many billion-dollar business, big industry. So it's a field of interest to work with. We can ask, where are the installations being done mainly today? If we take 2017, we see that China is very much dominating. More than half of the total installations were done in China, 2017. India is up and coming. You see this part here. European Union is the green top here, which has been dominating the thing, but it's sort of installation is fairly constant, let's say. So it's much driven by Asia, and particularly China, which is also producing most of the photovoltaics. So that's where it happens. Here is one interesting chart which tells you a little bit what has happened. And this is I started to work as a PhD student, let's say here, 1990. And then solar cell was a very academic thing. You could meet some very excited, engaged green people. They felt solar cell, but no one, industry was not listening at all. This was far away. And the thing was that it was nothing wrong with the technology based on silicon cells. It's a fairly good efficiency, stable and so on, but at the time, way too expensive, more than 10 times more expensive than to be competitive. And one figure of merit which one uses in discussing the cost is the production cost, and the unit is how much it costs to produce 1 watt in electricity. So we call that dollar per peak watt. And let's say the dream target here when I started, when people said this, to reach $1 per peak watt. So that means, for example, sunshine, a blue sky, you have 1,000 watts from the solar energy per square meter. So if you have 10% efficiency solar cell, you produce 100 watt per square meter. Now, if that square meter costs $100 to produce, you produce $1 per peak watt. That's the unit. And that was at this time way too, it was a dream, and we felt all the time this can never be realized with silicon cell because that's a very expensive way of producing them. So when I started to write my research proposal, we always started to say solar cells are interesting, it's renewable, but it's too expensive, and silicon can never make it. We need to do research on something else. That we cannot say anymore. So we have to do other proposals because silicon has become cheap. And that's something for me to say very, very drastic in a way. Couldn't believe it here. And things happened, as you see, it goes down here. And here somewhere 10 years ago or a little bit less, you see that we are down here to almost $1 per watt. And there is, if you look here, it's quite a dramatic change here. And very quickly. And that was China saying that now we start to really promote solar and also subsidize production, of course, from the Chinese state. And this took the PV world by a big surprise. I remember a meeting in Korea, and it was an industrial meeting, so Samsung had talks at silicon cells. I was supposed to say something about dye-sensitized cells. I came down in the breakfast. I saw people who were attending the conference. They had the badge on. I didn't know them, but I went to have breakfast with them, and they looked like they were on a funeral. They were extremely sad and quiet, and they said, we don't know what. So I felt something dramatic has happened while I was sleeping. So I asked, what's going on? I said, well, we don't know how to survive. We have a company in Japan, PV company in Korea, and now we see that China is just taking us out, basically. So it was really drastic, but it also meant that we have a lot of solar electricity installed, as you saw. So nowadays, silicon cells are produced at almost $0.3 per peak watt. So it's way even below $1 per peak watt. And that is at some places the cheapest way to produce electricity, given all other technologies. So in the Middle East, for example, if you want to produce electricity the cheapest way, you choose solar. So that's very, very interesting. Other technologies I will talk about a little bit. Thin films, big company in the United States, they aim at $0.2. Perovskite solar cell is also having a potential to go down to these things. And then you cannot produce electricity cheaper than that. So that's a big change which has happened. These are the current technology used. This is a polycrystalline silicon cell. You surely have seen them. At the commercial scale with these panels, you can get efficiencies at top 22%. The world record for silicon as a single cell is 26.5% efficiency. The theoretical limit for such a cell is 31%, so it's not far away from the theoretical limit. Thin film cells, there are typically two types. One is cadmium telluride, that's this First Solar. They are now making panels up to 20% and quite big areas, more than square meter. CIGS is copper, indium, gallium selenide, similar performance, let's say. So they're up and coming, but 95% of all solar cells today are based on silicon. So I'm coming into what we are doing in research. Dye-sensitized cell, this is the two examples where you can choose different dyes, so you have nice colors, transparency. So this is a window application. These are the perovskite cells, which you also work with here at the Institute. So I will go through them a little bit. But first, coming to the title, how can you make your own solar cell from the kitchen, basically. So here is what we did some years back. It was the International Year of Chemistry 2011, and we said from our lab in Uppsala, let's make a kit so everyone can make their own solar cell. And this became very popular. So colleges, high school in Sweden, we made 50, 60 of them, and they are still, I think, borrowed all the time and so on. The ingredients for this particular kit was made for laboratory exercises for high school. You need, this is something we provide. These are the contacts, electrical contacts. Of course, for a solar cell, at least one of the contacts must be also transparent, so you get the light into it. So these are conducting glass, as we say. It's a normal glass with a top layer of fluorine-doped tin oxide. That makes fairly good conductor, fairly good transparency, let's say. So that's our contacts. Then we have this white powder, which you may be a little bit careful if you travel with them, and people may think that you're doing something else, but it's very harmless. It's white paint, basically, a pigment, titanium dioxide. We have it here as the white paint is based on titanium dioxide. You have it in toothpaste, and you find it everywhere. We have a pencil here, Scotch tape. This is a solution with the iodide salt, so it's with what's called the electrolyte. And then for the lab exercise, they should build their own solar cell so they can drive this calculator by the solar cell and not by the battery. So that's what they should do, let's say. And here is how to do it. Well, there is one missing ingredient, actually, and that's the dye itself. So that's on purpose. We tell them that you go and find your own dyes somewhere. And of course, we give some ideas what they can look for. But something which is colored and they can make a solution of it, that's what they look for. So here is how to do it. You start with your contact, the conducting glass. You put the Scotch tape on the side here for two reasons. One is that you spread out this titanium dioxide solution, and you want a certain thickness of it. So one Scotch tape is 5 micrometer thick TiO2 layer, 2 Scotch tape 10 micrometer, and so on. So normally you take 1 Scotch tape. Then you deposit your slurry of the TiO2 and deposit it. You then take it into a step here, which is a sintering step. So you have an oven or a Bunsen burner in your chemistry lab and so on. You need typically 400 degrees for half an hour. And then you sort of bake it. And then you have a TiO2 layer, which is, you will see later, it's a porous system, high surface area, nanoporous electrode. And then you dip it in. This is the fun part of the lab, let's say, because this is the dye solution. And we tell the students, so you take your favorite. So in Sweden, of course, we like blueberries. I don't know, you take your Lithuanian favorite fruit. I don't know what it could be. Maybe blueberries too, I can imagine. In UK, of course, they chose tea. When I was a postdoc with Michael Gretzel, we had a wine testing, not tasting. Well, we tasted too, of course, but but we tested different bottles of wine, and one was particularly good, I remember, but of course no one remembered which one it was the day after. But you take this, whatever you take, and then you dip your TiO2 into it, and then you stain the film with this dye. And that's your dye-sensitization. That's the anode, the photo anode, the minus, let's say. You need a plus electrode, the cathode, and then you take graphite from your pencil. So you take the other piece of glass and just write with it with the pencil, and you have a carbon counter electrode, as we call it. Then you put your two glass electrodes together, clamp them, and fill up the interior with your electrolyte. So then you have an electrochemical cell, and then you apply your contacts and measure current and voltage when you shine light on it. So then you can see how good you are and measure your efficiency and so on. For the lab exercise, they needed also to realize that for driving this display and calculator, they need 1.5 volt. And the typical solar cell here gives 0.5 volts, so they have to series connect 3 or 4 to drive it. So that was the exercise. So here is how you can do your own solar cell in the kitchen, basically. a little bit of history of dye-sensitization. This goes back, and I think this is the first published thing about making what we call dye-sensitization. It has nothing to do with energy. It goes back to the technology of color photography. So before people, and we have forgotten how you make a color photographic film, of course, but the starting point was to use silver halides, and that's what we know today, a semiconductor. And when you illuminate that, you can get an electron in there, which you can then develop and get a picture. To make that from black and white to colored, you need some kind of dye molecule to absorb that kind of dye and expose it to make it a color photography. So people started to experiment on using dye on silver halide. So today we would say that it's a dye-sensitized semiconductor. And the first one is this James Moser in Vienna, 1887, saying that he used a natural occurring dye on a silver halide. And if you can read, it's in German, but here you see that he says he can measure 1/4 of a volt under illumination. I also like this paper because this is the complete paper. So very much to the point, I did this, I measured 1/4 of a volt, and then I thank my assistant for the help. That's what it says basically here. So something we should learn from how to write scientific papers. Go to the point and don't say too much. So you can read this quickly. Then it took almost 100 years before people starting to realize what is actually the process and how to explain it. And the credit goes mainly to the sort of father of photoelectrochemistry, Heinz Gierischer in Berlin. He and his group in a series of papers at the end of 1960s discussed this as an electron transfer process. So you have the dye adsorbed to the semiconductor surface. You excite the dye with an electron to the excited state, and then it's injected into the conduction band of the semiconductor where you can transfer it and collect it as a current. Then in the semiconductor you have a Fermi level, or in chemistry, electrochemical potential, and the difference of the Fermi level to the redox potential of the electrolyte makes the voltage of the solar cell. So that was explained in that time. Then we make another jump. Let's see, before something more interesting. It's a long story, and people realized that this is very difficult to do because people wanted to use high-quality semiconductors, and high quality also means a very well-defined surface. So you don't want any defects at the surface. You want a very smooth, compact semiconductor, preferably single crystal, a flat surface where you can put the dye on. But if you now use one molecular layer of dye, the probability to absorb light by one monolayer of dye is very low, maximum 1–2%. So visibly it will look like a window. It's completely transparent. Maybe a faint color of this monolayer of dye. So it's not enough to absorb a lot of light. So, and people was sort of focused, well, we can only have one monolayer to make this injection efficient. If we have multi-layers, we will not have injection. It will just recombine. So this was a dead end, basically, at the end of 1980s, until Grätzel and his group showed another way of getting more dyes on the surface, and that was to use high surface area electrode. But that was completely counter-intuitive to what people try to do. So Grätzel and Brian O'Regan published a famous Nature paper in 1991, and here is when I was visiting EPFL for the first time. And I remember Brian here, he made a heroic effort to make these porous electrodes. It took him some years to develop the recipe. But they made in one go, efficiency came up from much less than 1% in sunlight to 7%, an order of magnitude increase. And the most interesting thing was that it was based on a way of doing solar cell which you shouldn't do. It shouldn't theoretically work. So it was very exciting, of course, how can it work? I used to compare it with this surprise order of magnitude increase with something from sport, and I was thinking how to compare it. We were writing a review And then being interested in sports, this is before, well, I was 4 years old, so I don't remember the jump, but you can see it on YouTube. It's a fantastic jump by Bob Beamon. He took the world record in one jump with more than half a meter. And this was so surprising. You see the lady here, she don't even see him up here jumping. And it was so long that the measurement tape was not enough. It took them 1 hour to measure this long jump, and they had to find a new measurement tape to be able to measure it. And then came 890 as a world record. And it's still, of course, one of the longest ever made. So I wrote in the review, this was the Grätzel made a Bob Beamon-like increase in efficiency. The reviewer said, I don't know who Bob Beamon is. I think you should cancel that sentence. But of course, I kept it. I wanted to be there. These are the typical ingredients of a dye-sensitized cell from the starting point. This is from the early 1990s. This is what we can call a nano sponge in a way. It's 20 nanometer sized TiO2 particles. Its porosity 50–60%, being porous all the way down to the contact. So it's a high surface area electrode, and one monolayer of dye now can absorb 100% of the visible light at the absorption maximum. So now we can take care of all the sunlight absorption. The typical dye was a ruthenium complex, so it's a ruthenium metal with bipyridinium ligands, as we call them, and they are also having these carboxylic groups, and this was a thiocyanide ligands introduced by Grätzel group. This became the standard dye for 15 years, I would say. Although thousands of dyes were synthesized and published, this was one of the first one, and it was the best one for many, many years. It's interesting to think why it took so long time to find something. We have something better today, but this is a standard dye. The carboxylic groups here are important. They adsorb to the TiO2 surface. So that's how you sensitize, you anchor them to the surface. The typical electrolyte was based on iodide and iodine. So this is a cation and the iodide salt, and that's your redox couple. And this was the best redox couple for about 20 years. So very difficult to change. This TiO2 is, after almost 30 years now, still the best. You can imagine hundreds of publications with nanorods, nanofibers, zinc oxide, tin oxide, niobium oxide, all kind of oxide you can imagine. And nothing has come up better than the original thing. Here is the process a bit. We have this pore system. You have the dye molecules on the surface. You shine light on it. You excite the dye, and the electron is injected into the TiO2. And it goes through all these particles to the contact, do electrical work. It goes to the cathode, where you reduce the electrolyte, in this case I3- to I-, and then the electron is brought back to the oxidized dye, and you close the circuit. But here you can imagine all the material science you can do, different nanostructures, oxides, a lot of different families of dyes, a lot of redox system, solvents, can you make polymer instead of a liquid, and so on. So a lot of chemistry and physics to be done here. It's a very nice field in a way, because it really combines chemistry and physics, semiconductor physics, surface physics, and all the chemistry around it. So you really have to interact with experts in different fields, and that I think is one of the virtues of this research. A little bit on how we developed how this solar cell worked. This was the textbook before 1991, that you have a semiconductor in contact with an electrolyte. You form a Schottky junction, so you have a depletion layer at equilibrium, making an electric field in the semiconductor, and the band bending, as we call it. So when you excite the semiconductor, the electron goes in the electric field in this direction. The positive hole goes in the other direction and oxidize the redox electrolyte. And for this to be efficient, the textbook said you need a very good quality semiconductor. Surfaces is a place where you have losses, recombination, so avoid surfaces and avoid defects and so on. And you need this electric field to separate the charge and to transport them. And here came then this dye-sensitized cell, where we had no idea if it's doped or not. we spent 1 year of thinking, where is this? There should be an electric field to separate. We could measure that it works very well, but we were thinking, how does you separate the charge? Why is this electron so efficiently transported through all these nanoparticles? And why is not the high surface area a problem? It should be, according to the textbook. So for me as a PhD student, it was perfect, because we realized that the textbook doesn't give us the answer. So I didn't need to read any textbook. We had to sort of create our ideas from the beginning. So we took a much more chemist view on things. And for the charge separation, we studied the dye molecule in terms of quantum chemistry calculations, synchrotron radiation, mapping out the orbital structure. And the question was, when we excite the dye, where is the electron in the excited state locally? Where is the hole? And we could then, through this study, see that when we excite these kind of dyes, the excited state of the electron, this one here, is located on the carboxylic group. And that's perfect, exactly where we want it to be, because that's where we have the anchor to TiO2. And the hole is then the oxidized state is much located on these sulfur atoms on the ligand. So the view here is that the orbital structure of the dye helps us to separate the charge. When you excite the electron goes to the TiO2 side of the dye, and the hole goes to the electrolyte side of the dye. So the dye itself, just by its architecture, can separate the charge. We don't need the electric field. And then we also, of course, realized this is how we should design our dyes. They should be asymmetric. The electron goes in one part of the dye, hole goes to the other part. So that's the design structure of dyes, let's say, from that. The transport was also quite a fun story. After 1 year of inventing a lot of electric fields, which because people told us there must be an electric field, otherwise you cannot separate. Then at some point we said, well, forget about the electric field. If we just think that, well, the charge are actually going to the contact, and then they are taking out at the circuit. That means that the concentration of electrons are lower at the contact, that's where we extract them, than the concentration of electrons in the film. There's a higher electron concentration in the film than at the contact. That means a concentration gradient, and that is diffusion. So we said this is based on diffusion, not on electric field. So we then developed what we call the diffusion model, and that became quite a surprise, but today is the accepted way of thinking about it. And now it's more details, where are the electrons and how do they move and so on. But diffusion and charge separation in the dye is the way of explaining how it works. So a little bit on practice. I think the dye-sensitized cell today has a niche when it comes to design different colors. This is the Sony company in Japan making these lamps with let's say, artistic solar cells. This is the solar cell with the Japanese flowers. You can think about it as windows. This is in Austria. Lightweight on flexible substrates. This is in Switzerland, a company making these window facades. This was the BASF company making dye-sensitized cell in the car and so on. So there are some possibilities for applications still to be developed, let's say. Now I go a little bit into what we are doing in our research. So the question here now is, if we take the standard system we have, where is the main loss? How can we improve it? And the world record for dye-sensitized cell is based on this ruthenium complex and iodide, and it's 11.9%. So how to improve it? Well, we look into the energy levels. This is the HOMO, the ground state of the dye, excited state, conduction band. This is the redox potential of the electrolyte. And the voltage is given by the Fermi level difference to the redox potential. And here, when we map this and measure the numbers, we get quite a big loss here, a gap in potential between the redox potential of iodide to the oxidized dye. It's a gap of typically 0.7 volt. And that's a loss. It's a 0.7 volt loss in the system. And that's where we felt here we can maybe get more voltage out of the system. And what to do then? Well, we should change the redox couple, of course, to something which has a more positive potential. That means that you go more in this direction, lower energy. That means that you increase the gap, so with the Fermi level, so higher voltage can be expected. But you also decrease the driving force to regenerate the dye. So the regeneration driving force is, of course, the difference of the redox potential and this dye here. So by going in this way, you also slow down the kinetics here. So that's the drawback. So the question is, how far low can you go until you start to make this too slow, let's say, and you have recombination. The other problem, the reason why this was standing its time for 20 years was that for all other redox couple, if you change, you open up a recombination process. So electrons here in the TiO2 can also react with the electrolyte. And that works very well for all redox couples besides the iodide, which is not doing that. So that was a fundamental problem. When you change to something else, you have a recombination of electrons in TiO2 with the electrolyte. So you need to passivate that reaction. And I will make that very, very short. We managed in Uppsala to find a way that the dye itself can passivate that recombination. And we started to work on new redox couples. And here is the diagram again. Here's the redox potential of iodide and the gap to the oxidized dye here. And then we tried with the new dyes we developed, we could use cobalt complexes, and then you can increase the voltage by going this way. And nowadays we are focusing a lot on copper complexes instead, where we are really closing this gap to from 0.7 to 0.2 about. So we get voltages much higher than the iodide. And the reason we could do it is design of the dyes to passivate recombination. So this is a typical organic dye we are using. So that's what we are doing at the moment, and our published record value nowadays is 13%. We are trying now to certify that to show that we have a new world record. And these are now the dyes we are using, so it's not based on ruthenium anymore. We have designed them to get good efficiency, of course, but also to passivate this recombination by these alkoxy groups here. So that's the state of the art at the moment, I would say. One interesting aspect of this copper complex and organic dyes is that they work very well for indoor light, diffuse light. So if you have sensors indoor and so on to replace batteries, for example. There the dye-sensitized cell is giving the highest. This is the power output in microwatt per square centimeter, 15 microwatt per square centimeter with a fluorescent lamp at 200 lux. That's the unit for light intensity. This is what you have in here, I would say, about in light intensity, 200 lux. And you see here we compare this value with the best solar cell there is, and that's gallium arsenide, which has the world record of 29%. They are very expensive, but the best solar cell, and we are dye-sensitized, are even better than the gallium arsenide for indoor light, much better than silicon. And so here we think we have maybe the best technology for using solar cell for indoor applications. And the efficiency is even up to 32% now, but that's not the solar efficiency. It's a lamp efficiency. So it's the lamp spectrum which gives us this efficiency. And it's, of course, coming from Sweden. This is a lamp bought in IKEA. Of course, we have to be our Swedish promoters. So I think that's a chance for dye-sensitized cell in indoor light. And we work on trying also to improve efficiency for solar efficiency. Now, what you can do is, as I said, a lot of materials science. You can have new dyes, new absorbers, play with the electrolyte, different redox couples, maybe even different polymers and so on. And of course, people have done that a lot, and you can also replace the dye by some inorganic semiconductors like lead sulfide, cadmium selenide, and so on, and make them very small, so you even make them as quantum dot absorbers, and then you inject electrons by these. So that's an alternative. People also started to look into using solid instead of a liquid as a whole transporter instead of the redox electrolyte. And one classical material for such things is called spirometad or meotad. This is an organic molecule, and you impregnate it into the porous system, and it conducts holes, and it's in a solid amorphous state. So these were sort of ongoing a lot, and if you now take this spirometad together with an absorber with a perovskite structure, you come to something we call the perovskite solar cells. And the one who did this first is a good friend of mine. It's Tom Miyazaka. This violin cost, I think, $100,000 or something. It's a very expensive violin. He's a keen collector of information. This is Italian. He has published 2 papers on this violin, let's say, besides his perovskite papers. But that's a side story. But it's when we discuss what you do besides being a scientist, this is one example of what you can do as a hobby. He published and started to work on sensitizing TiO2 with a perovskite material. It's a methylammonium, that's an organic ion, lead triiodide. That was the starting point. And it was basically not very successful. He could measure 3% efficiency, so not very extraordinary. And he also said that, well, to measure it, I have to be very fast. I have to run from the lab to the solar simulator because stability is maximum 10 minutes. Then the perovskite dissolves into the iodide electrolyte. So it's gone in 10 minutes. He published that 2009, and not very much attention was paid to it. But 2 things happened. One was that Namgyu Park in Korea, he had worked with perovskite in his PhD for other reasons, but he felt perovskite I know about. I will try to repeat what Miyazaka is doing. Henry Snaith at Oxford had the same idea, but they also came up with the idea to, since the liquid electrolyte was the problem for stability, let's use this pyrometad, which is a solid hole conductor instead, and see if stability is improved. And that was the breakthrough, to use the perovskite as on the TiO2 and then the spiro molecule instead. And then the 2 group, Namgyu Park together with Michael Gretzel and Henry together with Tom Miyazaka published independently 2 papers in 2012 showing that you can use this perovskite material with spiro and get about 10% efficiency and not so bad stability. But then there was one thing more, which is the key thing in Henry Snaith's paper. He showed that you don't need to use injection. So the classical idea from dye-sensitized cell is that you excite the absorber, the electron goes into TiO2. He made a blank experiment, a reference to use alumina oxide instead, which is an insulator, cannot inject. And he could show that, well, the solar cell still works with my perovskite. So that means that the electron transport must be through the perovskite layer to the contact, not into the alumina oxide. So the perovskite itself can transport electrons. Edgar Lios was with Michael Gretzel at the same time. He's from Israel. He showed that I don't even need to use spiro. I can just put gold on top of perovskite, and it also works. So the holes are also transported efficiently as perovskite. So that tells you that this is not just a dye-sensitized cell. It's actually perovskite itself can work like that. And we can prepare it like we prepared it in the kitchen. It's solution processed. So that created a lot of excitement. And I think last year we had 5,000–6,000 papers published in perovskite. So it's a tremendous area and very challenging to be in. Here is what is a perovskite? Well, it's a structure. It's a cubic structure. You have your metal, that's the lead in our case, is in the corner of the cube. The cation, our methylammonium, is in the center. And then you have your halide in an octaeder around the lead. So that's the perovskite structure. It was first discovered of calcium titanate. So classical perovskites are oxides. In the 1800s, and it was discovered by Gustav Rose, and he named it after Perovskite, who is a Russian person. So it's a structure, and you can have several supraconductors. Maybe you have lectures here are often based on perovskite structures. We can let's see what. Here is then also the structure of. In our case, we use the starting point was methylammonium lead triiodide. It has a good band gap for solar light absorption, 1.5 electron volt. When you excite it, the separation is very efficient. It doesn't take any energy to separate electrons and holes. And the recombination of electrons and holes are slow enough that you can transport the charge efficiently to the contact. And this is, of course, a lot of questions. Why is it like that? How can we design it? And so on. So there's a lot of fundamental questions. But in short, it's a perfect semiconductor. Has all the criteria to be efficient for solar absorber. And you can make them in minutes in the lab, in chemistry lab. Of course, I'm exaggerating a bit because there are issues with reproducibility, humidity, if you have that. So it's a sort of seasonal solar cell. We have higher efficiency in the winter than in the summer, for example, and so on. So the controlled atmosphere is very important. But in principle, you can do it in your chemistry lab. This is one way of doing it. You start with the TiO2, perhaps. This is also a lot of different substrate. Now the TiO2 nanoporous layer is much, much thinner, just a few hundred nanometers compared to the dye-sensitized cell. You start from there, then you have maybe a solution of lead iodide in a solvent, EMF. You put that solution and spin coat out the solution, and then you form a lead iodide layer in the porous TiO2. Then you take a methylammonium iodide salt in another solvent, and then you convert to the methylammonium lead iodide on TiO2. So that's the simplest way of doing it. But you can do it with evaporation and other methods as well, of course. But this is how we typically do it at EPFL. There are also different possibilities for device structures. This is the memory of dye-sensitized cells. It's the TiO2 particles here impregnated in the perovskite absorber film. Typically now the TiO2 layer is 200 nanometers and the perovskite is half a micron. Then you have it on the contact, and you have then spiro, for example, as a whole contact, and then you put gold as a contact on the top. So you excite the perovskite, the electron goes to this side, and the hole goes through the spiro to the gold. But perovskite can conduct electrons and holes on its own, so you can basically take an electron contact and a hole contact and put perovskite in between, and they work as good, I would say. So that's the simplest structure and very exciting for practical reasons. And you can also turn it around, so you have a nickel oxide hole contact to start with, perovskite, and then on top an electron contact. So there are many variations to do this. And many applications are coming up, particularly LEDs is looked upon a lot with these kind of materials. Here's the excitement also because, as I said, it started with 3% with Tommy-Asaka, and then 2012 we had 9%, and then people start to certify. EPFL was early here. And then it was increasing, and today the world record is 23.7% from Beijing. We don't know how this is done yet. It's not published, but the value is there. So it's all just to tease us, of course, how to do it. But our best value in the EPFL is 22 to 23%. So we are trying, but it's tough. Silicon best world record is 26.5, and CIGS cadmium telluride is even lower than this one. So in just a few years, it has really become a contender, let's say. Coming to what we do a bit at EPFL, we started to look into the chemistry of the perovskite, and you can basically manipulate the composition. Lead is there, then you have the iodide halide. You can mix in bromide as another halide. That tunes the band gap, so you increase the band gap with bromide, but also make the quality of the perovskite a little bit better. You can also work on the cation. This was methylammonium. It's this ion here. You can also try to mix in formamidinium, and that's really what we want to have at the end. A little bit larger molecule. It shifts the band gap to lower values and also has other stability reasons better. Our goal is to have pure Fa actually, but then very difficult to make that into a pure perovskite structure. So there's a lot of things going on here in terms of forming the perovskite structure and how to get good crystallites in the absorber layer and so on. So the quality of the perovskite layer depends a lot on the composition here. But with this kind of mixed, this we call the double cation. I'll come back to that. 2 cations. With that kind of composition, my postdoc at the time, Dongxin Bi, took the world record at 21%. This came as a Christmas party. I think Marius had left us at the time, but we had a Christmas party here, and then this was announced the same minute. And I remember Michael Gretchen came into the party with his laptop. Now we have the world record, and of course it was a good party with such a thing. We were happy for 3-4 months. Because then the Korean group, Professor Seok, took it back. He had it before to 22%. And then actually we said, okay, there's another, you can change your game, let's say, you play another game. So this is 21% here is, you can be as small as you want. Size doesn't matter. If you want to have a world record to come into the journals, let's say, you must have at least 1 square centimeter size solar cell. So this is 0.1 now, let's say, very small. So we felt, okay, let's take the world record for 1 square centimeter. That's no one has really looked into. So we certified that 19.6%, and that was, we were happy for 1 week. Because then Sok took it back and said he's at 19.7%. So, but this is a little bit the race. But anyway, it's a bit fun with it. Now it's 23.7, as I said. Michael Saliba here and others continued in our labs to work on this composition. So he also added, it became like a sport almost. So how much can we add? Depends a bit to form the structure on the size of the cation. But cesium did well, and so this cesium was added to become the triple cation, and that improved things quite a lot. So we had higher efficiencies and also better statistics. This is the reproducibility, let's say, average values. So you see also triple cation compared to double cation, much better with the triple. Stability became better and so on. So that's still something we try to understand, why this mixed is such a good strategy. And we can say that one reason is that this is a cross-section SEM, and you have the perovskite layer with the grains, the crystallites like this, and what you don't want to see is a lot of grains with these grain boundaries where you may have recombination losses. So adding 5% cesium makes the perovskite film much more perfect, let's say, without grain boundaries and higher quality. The reason for that is still to be studied, let's say. But this mixed is a strategy we are working with. And of course, Michael couldn't help, so he said, let's add a 4th one, and the next one in line is rubidium. So this became the quadruple mixed cation, and that we published with our best value published so far. So we had, with that, 21.6%, good stability, very high open circuit voltage, almost close to the theoretical limit. So that means a very high quality absorber and so on. And this was interesting because a high voltage also means that it should work as a good LED. This red spot here is the solar cell in reverse. It works as an LED. So we inject current and get light out, let's say. And that's a feature of a high quality material. So it has all the virtues for also LEDs. I'm coming to the end because I'd like to mention a little bit also on stability, because this, as I said, was in the beginning 10-minute stability. How does it look now? And there are all reasons to think that it's difficult to get it stable. We investigated the stability and saw that high temperature was really killing the devices. When we took it to 85 degrees, the efficiency dropped from 18, 19 to 3, 4. Completely dead, almost. And we thought, okay, now things are problematic. And the perovskite, the ions are moving. We made a SIMS profile. That means that we can look at the elements we have throughout the device. So here is the contact. We have the gold layer. We have the spiro. Then comes the perovskite layer, TiO2, and the conducting glass. And to our surprise, the problem of stability was not perovskite. It was the gold contact. So gold diffused through from gold even into the TiO2 layer. So gold is problematic. So that we have to avoid, or to gold on spiro, I should say. So spiro is that. So solving that problem, to replace spiro with a polymer, we could get this stability at 85 degrees. We start here, put it take it to 85 degrees, illuminate it for 500 hours. It's running and operating as a solar cell all the time, and we are almost keeping the same efficiency as we started at 85 degrees. So that's very promising, let's say. So I think there is reason to of course, be worried about stability, but for sure there are possibilities too. This was in a group with Italy who took our solar cell and encapsulated them in a clever way, also to protect it from UV light by fluorescent molecules to convert UV to visible light. And they measured stability outdoors, for example, here for half a year in Torino. So this is stability data over half a year, well, not here 3 months, but they tested for half a year and looked stable. So I think, I wouldn't say it is stable because there are more things to it, but we can at least not say that it's not stable. That's, I think, is the state at the moment. So another just exciting things which comes up sometimes of surprise is that what we saw in our stability data is that in the first minutes there is a drop. But then and then we thought this is a degradation and it stabilizes. But then we saw that if it takes a rest, a good night's sleep, we are back next morning where we started. So this is reversible. And also something of research to look into. What is this initial degradation, which is not a degradation in a way, because when it rests, it comes back. So it's something, ionic motions and so on. But it also puts us to think how to do accelerated stability testing. So if you do it for many hours, you may have this kind of curve. But if you make it rest, you keep a higher level of efficiency. So that's a question. This is just to say also that one way of commercializing perovskite is to put them on top of existing silicon cells. So then you take perovskite as one absorber layer, you absorb the high energy photons, then you let the low energy photons be absorbed by the silicon, and in this way you have 2 absorbers and your efficiency can be theoretically higher than the single absorber. And this is people doing, and the world record is 28% from a company called Oxford PV. So this is now higher than the best world record silicon. So that makes these tandem devices very interesting. Yeah, I think I have to finish. So in summary, on dye-sensitized cells, I told you a little bit how you can make them and promote them in laboratories. What we are doing to try to make them more efficient, and also commercialization efforts in terms of design and colors. I didn't say much. We do also some hydrogen and so on, solar fuel. Perovskite cells, does it compete or actually even join silicon cells in tandem devices for the future? A key thing is stability to prove that. And I was introduced being a member of the Swedish Academy, and the thing with that, if people are curious, is that it gives out the Nobel Prize. So of course people ask, so how do you get the Nobel Prize? I cannot say anything really. We are confidential for 50 years. So but I can tell you, if you want your country to get more Nobel Prizes, you should tell your government to eat more chocolate. So this is the correlation between the number of Nobel Prizes in one country and how much chocolate they eat. Let's see. Very clear correlation, as you see. So of course Switzerland eats a lot of chocolate, and very high up here, and then you have almost like a straight line here. So that's the trick. So please take some chocolate for a coffee break, and with that I thank you for your attention.
Thank you very much for the very interesting talk, and probably some questions. Who would like to?
Thank you for this very interesting talk. Just short question in order to compare different kinds of the cells. How do you estimate the possible price for perovskite watt? And the second question, what is the time of the degenerating of the silicon cells and films as well?
So the first question was about perovskite.
The price for
yes, watt. Of course, yes. Well, as I said, I think if there are estimations of the price, it seems to be able to be lower than $0.2 per peak watt, which would make it competitive or even cheaper than all other technologies. The reason is that from a materials point of view, it's the glass substrate which will cost some money. And upscaling, you can think about screen printing and different inkjets people are trying. The thing there is that silicon is so cheap nowadays that to compete on price is not enough, I would say. So you need to have something which is higher in efficiency. So if you take a cost for the total system, because then you also have to include the installation cost on the solar panels. You convert DC electricity from the solar to AC, that's converters, they cost money, and all other parts. So the system cost makes that the rest, besides the solar cell, the other cost is more than half nowadays. And that means that for the solar cell to sort of make any change, it's better to work on higher efficiency than lower price of the solar cell. Of course, the price has to be low, but the efficiency is more important. So that's why this tandem efficiencies is very important, that you can show that tandem cells can be more efficient than the best silicon cells to boost the efficiency. So that's what we hope for, let's say. But I would say that we have to push the efficiency, that's key. And then for degradation of silicon cell, companies guarantee 20-25 years. So you get that as a guarantee from when you buy them. And one company said, well, we can guarantee 50 years and so on, but they were not allowed to, it was too long, the people. So as far as I know, the guaranteed lifetime for commercial silicon is more than 20 years. That I don't know exactly, but I think it should be similar. It has to be, otherwise it's also difficult to compete. Yes. So that's the challenge for perovskite. If you put them on tandem, you have to have the same lifetime as the silicon. That's a very key issue.
Some more questions?
Yes, thank you, Mr. Hagfeldt, for this very stimulating talk. I had a question slightly related to your talk about how, you mentioned that changing the structure just by mixing the perovskite, for example, implementing formamidinium to improve its effectiveness. What's your opinion on changing the lead cation with, say, tin? Since, so far efficiencies are lower, yet the reason for doing so is, some sort of environmental, concerns.
Yeah. So the most difficult one to replace, unfortunately, is lead, and there is really no contender there. Lead seems to be a magic element. As far as I know, the best replacement is tin, as you mentioned. At 9-10% efficiency, I think. The problem with tin is that it easily oxidizes. So you have tin 2+, and it oxidizes to tin 4+, and then you're dead, basically. And then it would mean that to properly make a tin oxide, you would need to do it without any oxygen or perfect encapsulation. So this is the big problem with tin, the stability of it. And I'm not sure you can get around it. And then, of course, you should have the same efficiency. Also, tin is not really that harmless. It has also a toxicity, actually. So I'm not sure tin is the right way to do it. People are then trying to mix, replace with, for example, you have lead 2+, and one way of simulating, let's say, your 2+ species is to take one 3+ and one 1+ to mix. So silver indium, for example, is a mixture people are trying, but that is still very modest in efficiency at 1-2%. So we are far away from replacing lead, unfortunately. On the other hand, the lead issue is perhaps more, what can I say, maybe political is not the right word, but it's very little lead. So if you calculate, if you say that you have some square meters of lead and all the perovskite in some sort of disaster is dissolved by rain and every lead goes into the soil, that amount of lead does not really change very much the background level of lead in the soil. So in principle, I don't think it's so much of a problem. But of course, there can be legislation saying that you have to have zero lead, and that's it. So we have to look for. Yeah. So I mean, there can be exceptions like that. So, but of course, a very important research is to find replacement of lead. But I would say today we are just exploring possibilities without really knowing where to go.
Some more questions? I have one more question. Yeah. So you initially talked that you can produce a solar cell dye-sensitized with any dye. So it means that titanium dioxide can withdraw electron from any excited molecule?
Yeah, that's a good question, because that's not really true, of course. Not every dye works. So there are some criteria for a dye to work. One is that it should adsorb to the TiO2 surface. Natural dyes are typically having some oxygen and carboxylic groups, so they do absorb. Strawberries do not absorb, for example. So I think so strawberries does not seem to work very well. The other criteria is that the excited state has to be higher than the conduction band, so the electron is injected to the TiO2. If it's lower, it will not inject. So that's another criteria for a dye to work. I know a story when Michael Gretsen told it. He was in Helsinki, I think, to give a talk, and somehow they asked, they should do their own solar cell. So he pointed to, he had taken some fruits with him on to use, but somehow during transport something happened with them and they didn't work. But then he found in the coffee break some cherries, and then let's try them, and then it worked again. No, it's a lot of fun with it, actually, yes.
Okay, thank you once more for the very interesting lecture.
Thank you very much.
And this small present from organizers.
Oh, great. Thank you very much. Yes, thanks.